This is your presenter Asloob Mudassar, and I am presenting slide number 106 of the course on laser physics. Question is, what is electron impact excitation? Find an expression for the corresponding pump rate. The answer is, in the electric pumping process, electrons may undergo elastic and inelastic collisions. During inelastic collisions, the atoms of the pumped gas may either be excited or ionized. The electron energies should be such that the gas atoms are excited to the desired excitation level. For example, the upper laser level. This type of excitation may be referred to as the impact excitation. That is the excitation by electrons to the desired laser level, that is to the upper laser level, will be called impact excitation. In order to derive the pump rate equation, we assume that a collimated beam of monoenergetic electrons passes through the gas. Let Fe is the electron flux of the beam, measured at a plane located at z is equal to 0. That is at the starting point of the active medium rod or active medium cylinder or the container containing active medium perpendicular to the beam. So we have defined Fe at a plane which is perpendicular to the beam. The change in flux dFe when the beam travels a distance dz in the material is given by dFe, that is the change in flux, is equal to minus sigma E times Nt times Fe times dz. And this negative sign is due to the fact that Fe will decrease with the distance z. So we have a negative sign over here. Fe is a measure of the number of electrons per unit area per unit time. Sigma E is the total electron cross-section. Nt is the total number of populations of the atomic species. Sigma E is composed of both elastic and inelastic cross-sections. The elastic cross-sections will be represented by sigma E1 and the inelastic cross-sections will be represented by sigma E2. Our further investigation will be around inelastic collisions, that is, we shall discuss inelastic cross-sections because we want that our electron beam should impart energy to the atomic species and make them to go to the higher states, that is in the excited states. And dz I have also explained that it is the distance that the electron beam will travel through the active medium. For example, through the gaseous state of the active medium through the gaseous state of the laser material. Sigma E2 is the cross-section of the transition from ground level to the upper laser level. The population rate of the upper laser level due to the pumping process is defined as dN2 over dt, that is the rate of change of N2 population due to the pumping process P is equal to sigma E2 times Ng times Fe, where sigma E2 has already been explained, that is it is the inelastic cross-section. That is the sigma E2 is the inelastic cross-section. Ng is the population in the ground state and Fe is already explained, that it is the electron flux. You see that we are using N2, it means that we are considering the only two level atoms in which we are pumping to the level number 2 and we are regarding the level number 2 as our upper laser level. And we have given an expression on the right hand side, which is a sigma E2 multiplied by Ng multiplied by Fe. Now Fe can be decomposed into Ne multiplied by V, where Ne is the electron density in the collimated electron beam, and V is the velocity of the electrons in the beam. Here we are using single value of V. It means that we are assuming that our electron beam, our collimated electron beam is monoenergetic. That is, all the electrons have the same kinetic energy. And Ne is of course the electron density. So we have replaced Fe in this expression by NeV, by the product of electron density multiplied by the velocity of electrons. And here we are assuming that the electrons are monoenergetic. That is, they have the same kinetic energy. Now we have rearranged the terms. We have written Ng into times Ne, and we have combined V multiplied by sigma E2. Ne is the electron density in the collimated beam, and V is the velocity of electrons in the beam. Sigma E2 is a function of energy E in the collimated beam. That is, sigma 2 can be written as sigma E2 as a function of E, capital E. If the beam is not monoenergetic, E will not be a single value, but will have a distribution of energies, or equivalently distribution of velocities. So equation number 106.2 can then be written as. So you see that we are now writing the pumping rate equation. That is, the pump rate represented by Rp is equal to the dN2 over dt due to the pumping process P is equal to Ng into Ne multiplied by V time multiplied by the average of the V into sigma E2. You see that here we have considered the average value. In equation number 2, we have just written V times sigma E2, because here we were considering that our electron beam is monoenergetic. But in equation number 3, we are considering that the electron beam is not energetic. So the electron energies are so we shall have an energy, and so we shall have a distribution of energies, or equivalently we can say that we have a distribution of velocities. So we need to calculate the average value of the product of V and sigma E2. In obtaining this equation, we have replaced Ng by Nt, which is appropriate for a multi-level laser system, in which the lower laser level is not a ground level. So you see that here we are, since we are considering only two laser level systems, we are writing the pump rate equation. That is, we are pumping the atoms to the upper laser level, which is the N2 level. And here we are saying that the our ground level is Ng level. But here we are also assuming that our ground level is not a single level, but it is composed of many sub-levels coupled together. And the population of all the levels in that ground state will be equal to Nt, where Nt is the total population present in all the sub-levels of the ground state. So Rp is the pump rate and Rp is the pump rate. Now you see that if F of E gives the energy distribution of the discharge electrons, then the average is computed as given. Now you see that the next point is that we have to compute the value of the average value of V into sigma E2. For that one, we are considering distribution and the distribution of electron energies, that is represented by F of capital E. So now we are going to calculate average value of sigma, average value of V times sigma E2, which is given in the next slide. So the average value of V into sigma is equal to the integral of V multiplied by C multiplied by sigma as a function of E, and multiplied by F of E, which represents the distribution of electron energies, and then we are multiplying with the dE. So if we evaluate the integral on the right hand side, we can find out the average value of V times sigma. This integral can be computed if the electron impact cross section represented by sigma as a function of E, and the velocity distribution function F as a function of E are known. So if these two quantities are known, we can easily calculate the average value given on the left hand side. Now we discuss the electron impact cross section. That is, we are going to do further discussion on the value of sigma E, electron impact cross section. Assume that an atom of the gas is in the ground state with a wave function u1, and that the atom is raised to an upper state with a wave function u2 after collision with an electron. Let the incident electron is described by a wave function e to the power iota k naught dot r, where k naught is the electron wave vector and r gives the position of the electron measured from the center of the nucleus. After collision, the electron is scattered with a wave, with a plane wave represented by e to the power iota kn dot r, where kn is the wave vector of the scattered electron, and k in both cases is equal to 2 pi over lambda, where lambda is the de Broglie wavelength of the electron and is found from the expression, that is lambda is equal to 1.23 divided by the square root of v. For lambda to be in the nanometer, it is required that the electron energy capital E, capital V should be measured in electron volt. So if you insert the electron energy in electron volt over here, you can compute the de Broglie wavelength of the electron. During electron impact, there exists an electrostatic repulsion between the incident electron and the electrons of the atom. This interaction may be assumed weak with a very small probability of atomic transition. So let me read this paragraph again. During the electron impact, there exists an electrostatic repulsion. Notice this point. There exists an electrostatic repulsion between the incident electron and the electrons of the atom. This interaction may be assumed weak with a very small probability of atomic transition. The transition rate or the transition cross section is given by. So sigma E is proportional to the absolute square of the integral containing the product of u2 e to the power iota kn dot r, that is the complex conjugate of this quantity multiplied by the u1 e to the power iota k naught dot r, and the integration is performed over the volume element dv. And then we can write this quantity in the more simplified form as this one, that is the absolute square of the integral of complex conjugate of u2 multiplied by e to the power iota delta k dot r multiplied by u1 and dv. So we have represented the two k, that is kn and k naught, and we have written them as a simple delta k, where delta k is equal to k naught minus kn, where u2 is the wave function associated with level number 2 and u1 is the wave function associated with level number 1, and we have multiplied u1 with e to the power iota k naught dot r, that is the representation of the wave of the plane wave corresponding to the electron beam before collision, and we have multiplied e to the u2 by e to the power iota kn dot r, which is the wave, which is the plane wave represented by the electron beam after collision. And we have combined, and on the right hand side we have written it in the form of e to the power iota delta k dot r, where delta k is equal to k naught minus kn. If the incident electron has energy of the order of a few electrons, then the wavelength corresponding to the electron beam, that is the de Broglie wavelength, will be much larger than the dimensions of the atom A. So we have written that lambda is much greater than A, or much greater than A when the electron beam is of the order of a few electron volt. And lambda can be written as 2 pi divided by absolute value of delta K, where A is the atomic dimension. So if an electron beam has an energy of the order of a few electron volt, then the de Broglie wavelength corresponding to such electrons will have a wavelength lambda much greater than the dimensions of the atom, where A represents the atomic dimensions. So if you write this equation, that if you represent A by the value R, then you can multiply it by delta K on the other side, and delta K dot R will be smaller than 2 pi, or we can say that delta K dot R will be in principle is much less than 1. The R, which is the distance of the electrons from the nucleus, the maximum distance is of the order of A. So we can write that the absolute value of R cannot exceed the value of A. So absolute value of R is always lesser than equal to A. E to the power iota k dot R can then be extended as a power series of delta k dot R. So you see that since we have e to the power iota delta k dot R present in the integral in equation number 106.5, we need, if we wanted to solve this equation, that is the integral in this equation, in equation number 5, we need to expand e to the power iota delta k dot R in terms of a series containing delta k dot R. So e to the power iota delta k dot R can then be expanded as a power series of delta k dot R. U1 and U2 are being orthogonal. That is, U1 and U2 are independent of each other. They have different, their energies are independent of each other. And the spin of these two states are also independent of each other. That is, they have different spins. And the orthogonality means that they are independent of each other, and their inner product is also equal to 0. So here we have u1 and u2 being orthogonal. We need to consider only the first term in the expansion, which is non-zero. So the first term in the expansion is non-vanishing in this case when u1 and u2 are orthogonal. So you see that if you expand e to the power iota, if you expand e to the power iota k delta R, then you need to take only the first term of that one. So we are substituting the first term in equation number 5, and we have this integral, that is sigma e is proportional to the absolute square of integral of conjugate of u2 multiplied by the vector r multiplied by u1, and of course integration with respect to volume element dv. So we need to calculate this integral, and you know that if you identify this integral is nothing but mu to 1, which is the electric dipole moment of the transition from state 2 to state 1. And we have, and of course this is here it appears in the form of the absolute square of mu to 1, where mu to 1 is the electric dipole moment of the atom. When mu to 1 is not equal to 0, then it means that the optical transition is allowed, because the value of a mu, the non-zero value of a mu to 1 to be non-equal to 0, to be not equal to 0, represents that the optical transition is allowed. That is, the electron impact cross section is proportional to the photon absorption cross section. So since the optical transition is allowed, the electron impact cross section, which is here is you see that on the left hand side we have written electron impact cross section sigma e, and on the right hand side we have obtained an expression which is optical, which is the absorption cross section of the photon. So this is mu, this absolute square of mu to 1 represents the photon absorption cross section, and on the left hand side we have the electric, we have the electron impact cross section. So electron impact cross section here is proportional to the photon absorption cross section. A transition with a high optical transition cross section means that the electron impact cross section for the transition would also be high. So if mu21 has a larger value, which represents the optical transition, which represents the photon absorption cross section. So if this value is higher, then of course sigma E will also be higher. That is, the electron impact cross section will also be higher in that case. So you see that in the last paragraph we have discussed that mu21 is not equal to 0. And then we have listed only, then we have expanded the exponential factor only by the first term. And we have obtained mu21 on the right hand side, which represents the absorption cross section of the transition, mu21. And on the left hand side, we have electron impact cross section. So here we have a relationship between the two. So if mu21 is greater, is larger, then of course sigma E, that is the electron impact cross section, will also be larger. So this was the case when mu21 is not equal to 0. Now if we consider mu21 to be equal to 0, which means that the transition will be optically forbidden. That is, by optical means we cannot achieve this transition. And also if delta S is equal to 0, that is no change in multiplicity. That is, the both states, in the ground state and in the upper state, the multiplicity is the same. And you know that multiplicity is given by capital M is equal to 2s1 plus 1 for the ground state, and for the second state we shall have a multiplicity M2 represented by 2s2 plus 1, where S is the total quantum number or total spin quantum number. So here we are assuming that the multiplicity or the total quantum number in the ground state and in the upper state is the same. So delta S is 0. That is no change in multiplicity. If delta S is equal to 0, it means that the spin quantum numbers are the same for the ground state and for the higher state. It means that the multiplicity which is given by 2s plus 1 is also the same for the ground state to the higher state, and so we can say that no change in multiplicity. So multiplicity actually gives you the possible states represented by the spin quantum number S in relation with the angular quantum number capital L. Okay, so if we are considering that mu21 is equal to 0, that is, we are considering an optically forbidden transition, and we are also considering that delta S is equal to 0, that is, there is no change in multiplicity, that is, the both states, that the lower state and the upper state have the same spin quantum number, then the next term in the expansion of e to the power iota delta k dot r, that is the next term, which is equal to minus square of delta k dot r divided by 2 will be non-vanishing, and equation number 5 will take the form. So you see that if mu21 is equal to 0, for example, if you consider mu21 equal to 0, it means that the first term has a 0 contribution. It means that we need to consider the second term. And if we consider the second term under the condition that delta S is equal to 0, then the second term or in the expansion of e to the power iota delta k dot r will be equal to minus times the square of delta k dot r divided by 2, and this second term will be non-vanishing. The first term, the contribution from the first term will be 0, the contribution from the high terms will be 0, so only the contribution from the second term, which I have shown over here, that is this term, will have a non-vanishing term. So under that condition we can write the integral, that is, we can write this integral by using the second term in the expansion of this can be written as shown in equation number 7. This sigma E may be regarded as a sigma forbidden. because this sigma E corresponds to the optical transition which is forbidden. So we may regard sigma E as sigma forbidden in this case. But you see that sigma E is the electron impact cross section, and sigma forbidden means that this transition is forbidden optically. So that's why we have related this one, that this sigma E may be regarded as sigma forbidden. It has been found that the sigma forbidden, that is the ratio of the sigma forbidden to the sigma allowed for electron impact excitation, is 2 orders of magnitude higher than the same ratio for photon impact excitation. So you see that if the forbidden, if the transition is optically forbidden, for example, as in this case we are discussing that the optical transition is forbidden. So optical transition, if we want to achieve the optical transition, it will not be possible for us. But you see that at the same time, this transition, to achieve this transition, which is optical forbidden, to achieve this transition by electron impact is easier, and it has a probability which is 2 times, which is 2 orders of magnitude higher than the same ratio for the photon impact excitation. So the ratio of sigma forbidden to the sigma allowed for the electron impact excitation, it has an order of magnitude twice that of the photon impact excitation. 2 orders of magnitude mean 10 to the power 2. Thus, the excitation to a forbidden level in a gas is more easily achieved with the electron impact excitation than with the photon impact excitation. So you see that in the lasing process, if we want to excite the ground species to the laser level, to the upper laser level, which is forbidden optically, then of course the only choice to excite to have such an excitation is through electron impact excitation, because optically that is forbidden. If optically that is forbidden, then the only option with us is the excitation through electron impact, because the electron impact excitation has a 2 orders of magnitude greater ratio than compared with the optical, that compared with the photon impact excitation. Now the next case we are going to discuss, that if mu to 1 is equal to 0 and delta S is not equal to 0. In the upper one, you see that in the previous case we have considered delta S is also equal to 0, so we considered that only the second term is non-vanishing. But you know that if delta S is also not equal to 0, then of course all the terms in the expansion will contribute 0 to the sigma E. So if mu to 1 is equal to 0, delta S is also not equal to 0. That is, there is a change of a multiplicity when the transition is done from the ground level to the upper laser level. And if there is a change of a multiplicity, then of course sigma E, that is the electron impact cross section, will be equal to 0 for any order of expansion of this. So if you expand all the terms in the expansion of this one, will contribute to 0. The incoming electron through the electrostatic interaction will couple to the orbital motion of the atom. So you see that here an important thing, that still we can have a transition, but what is the reason behind that transition is the incoming electron through the electrostatic interaction will couple to the orbital motion of the atom. The total spin of the atom and the incident electron must be conserved. So under this condition, we can say that the incoming electron will replace the electron of the atom undergoing transition, and the electron of the atom is ejected. So you see that this is a very special case and also a very rare case that we are considering, the case when mu to 1, that when mu to 1 is equal to 0 and delta S is also not, and delta S is not equal to 0. So all the terms in the expansion of e to the power iota k, iota delta k dot r will contribute 0. So sigma E will be equal to 0. But there is one possibility that the incoming electron through the electrostatic interaction will couple to the orbital motion of the atom. The total spin of the atom and the incident electron must be conserved. And in that case, the incoming electron will replace the electron of the atom undergoing transition, and the electron of the atom is ejected. The two electrons must have opposite spins for this transition to occur. The exchange of electrons occurs with a higher probability if the energy of the incoming electron is closely resonant with the transition energy. So you see that we can have an increased or higher probability for this reaction to occur if our electrons in the incoming beam has an energy which is very closely related to the resonant energy of the transition. Thus, we can write that the ratio of the sigma forbidden to the sigma allowed for the case of delta S, which is not equal to 0, is greater than the same ratio when delta S is equal to 0. So you see that we have discussed all the possibilities because the three possibilities arises. One in the expansion of e to the power iota delta k dot r, and we have discussed all the three possibilities. So we have discussed the contribution of the first of the expansion of this one to the first term. We have also discussed the contribution of this one to the second term, and we have also discussed the contribution when the all the terms in the expansion would not contribute. And in that case, we have also discussed the probability that when the incoming electron will have electrostatic interaction, will couple the incoming electron through the electrostatic interaction will couple through the orbital motion of the atom, and the transition in this case can also occur. So we have we have discussed all possibilities, all the three possibilities of electron impact excitation. So this is the end of slide number 106.